NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math lesson on homogeneous polynomials. Today we'll explore what makes a polynomial homogeneous and examine some important properties of these special expressions. Let's start with the definition. A polynomial is called homogeneous or of the same degree when all of its terms have the same degree. This means the sum of the exponents in each term must be equal. Let's look at our first example. Consider this polynomial p of a. b equals 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth power. To verify if this is homogeneous, let's check the degree of each term. As we can see, each term has the same total degree of 4. The sum of the exponents in each term equals 4, so this is indeed a homogeneous polynomial of degree 4. Let's look at another example. Here we have p of x. Y equals x to the fifth power minus 3x to the fourth power times y plus 2x squared y cubed minus 6x y to the fourth power. Again, let's verify if this polynomial is homogeneous by checking the degree of each term. Again, we can see that each term has the same total degree of 5. So this is also a homogeneous polynomial, this time of degree 5. Now, let's look at an important property of homogeneous polynomials. One of the key features of a degree and homogeneous polynomial is that if each of its variables is multiplied by a constant k, then the entire polynomial gets multiplied by k to the power of n. Let's apply this property to our first example. For the polynomial p of a, b, which is homogeneous of degree 4, if we replace a with k times a and b with k times b, then according to our property, we get p of k, kb equals k to the fourth power times p of ab. Similarly, for our second example, the polynomial p of x, y is homogeneous of degree 5. So p of kx, ky equals k to the fifth power times p of x, y. Let's verify this property for our first example. If we substitute ka for a and kb for b in our original polynomial, we get 4 times k a cubed times kb plus 6 times k a squared times kb squared plus 4 times k a times kb cubed plus kb to the fourth power. We can simplify this by distributing the powers. This gives us 4 times k to the third power times a cubed times k times b plus 6 times k squared times a squared times k squared times b squared plus 4 times k times a times k cubed times b cubed plus k to the fourth power times b to the fourth power. Further simplifying by combining the powers of k, we get 4k to the fourth power times a cubed b plus 6k to the fourth power times a squared b squared plus 4k to the fourth power times a b cubed plus k to the fourth power times b to the fourth power. Factoring out k to the fourth power, we get k to the fourth power times the original polynomial p of a, b, which confirms our property. In summary, a homogeneous polynomial is one where every term has the same degree. And when we replace each variable with that variable multiplied by a constant k, the entire polynomial gets multiplied by k raised to the power of the polynomial's degree. This is an important property that helps us identify and work with homogeneous polynomials in various mathematical applications. Welcome to our lesson on symmetric polynomials. Today we'll learn what makes a polynomial symmetric and explore some examples. A polynomial with 2 or more variables is called symmetric if the polynomial remains unchanged when any 2 variables are interchanged. Let's look at our first example with 2 variables. Consider the 2-variable polynomial p of a and b. P of a, b equals 3 times a squared plus 3 times b squared minus 2 times a times b plus 1. To check if this is symmetric, we swap all occurrences of a with b and b with a. This gives us p of b equals 3 times b squared plus 3 times a squared minus 2 times b times a plus 1. Rearranging the terms. 3 times a squared plus 3 times b squared minus 2 times a times b plus 1. Since p of a, b equals p of b, a, this polynomial is symmetric. Let's understand what makes a polynomial symmetric. In our example, the terms a squared and b squared have the same coefficient, 3. The term ab appears as negative 2ab, and swapping variables doesn't change this term. The constant term 1 is unaffected by variable swapping. For 2-variable polynomials to be symmetric, coefficients of similar terms like a squared and b squared must be equal. Now, let's look at polynomials with 3 variables. A polynomial with 3 variables is symmetric if it remains unchanged under any permutation of the variables. For example, a three-variable symmetric polynomial p of x, y, z would satisfy p of x, y, z equals p of y, x, z which equals p of z, x, y, and so on for all possible arrangements. Let's examine a concrete example with three variables. Consider the polynomial q of a, b, c equals a cubed plus b cubed plus c cubed plus 3 times a times b times c times the quantity a plus b plus c. To verify if this polynomial is symmetric, we need to check if it remains unchanged under any permutation of variables. Let's swap a and b. Q of b, a, c equals b cubed plus a cubed plus c cubed plus 3 times b times a times c times the quantity b plus a plus c. Simplifying, we get b cubed plus a cubed plus c cubed plus 3 times a times b times c times the quantity a plus b plus c. Rearranging the terms, we get a cubed plus b cubed plus c cubed plus 3 times a times b times c times the quantity a plus b plus c. This matches our original expression, so the polynomial is unchanged when a and b are swapped. To confirm the polynomial is fully symmetric, we would need to check all other permutations as well. But due to the structure of this polynomial, we can see that it treats all variables equally. Each variable appears as a cubed term with coefficient 1, and the product of times b times c is multiplied by a plus b plus c, which is also symmetric. Therefore, q of a, b, c equals q of b, c equals q of c, ab. The polynomial is indeed symmetric. Symmetric polynomials are important in various areas of mathematics. They appear in the theory of equations, particularly when working with roots of polynomials. Elementary symmetric polynomials form the building blocks of all symmetric polynomials. The fundamental theorem of symmetric polynomials states that any symmetric polynomial can be expressed as a polynomial in the elementary symmetric polynomials. Let's summarize what we've learned about symmetric polynomials. A polynomial is symmetric if it remains unchanged when any variables are interchanged. For two-variable polynomials, terms like x squared and y squared must have the same coefficient. For 3 or more variables, the polynomial must remain unchanged under any permutation. Welcome to our video on symmetric polynomials. Today, we'll learn about the properties of symmetric polynomials and how to express general expressions in terms of the basic symmetric polynomial forms. A symmetric polynomial is a polynomial that remains unchanged when any of its variables are interchanged. For example, a polynomial p of x and y is symmetric if swapping x, and y doesn't change the value of the polynomial. Let's look at some important properties of symmetric polynomials p of x and y. Property 1, a symmetric polynomial p of x and y can be expressed in terms of x plus y and x times y. Property 2, with each cyclic transformation, symmetric expressions transform into other symmetric expressions. Now, let's work through an example. We're given the expression s equals x cubed times quantity y plus c, plus y cubed times quantity x plus c, plus z cubed times quantity x plus y, plus x times y times z times quantity x plus y plus c. Let's express this in terms of elementary symmetric polynomials. Let's start by regrouping the terms. We can rewrite this as the sum of x cubed y plus x cubed z, plus y cubed x plus y cubed z, plus z cubed x plus z cubed y, plus x squared yz plus xy squared z plus xyz squared. Now, let's rearrange these terms to group similar structures. We get x cubed y plus x cubed z plus x squared yz, plus y cubed x plus y cubed z plus y squared xz, plus z cubed x plus z cubed y plus xyz squared. We can factor out common terms from each group. This gives us x squared times quantity x, y plus xz plus yz, plus y squared times quantity x, y plus xz plus yz, plus z squared times quantity x, y plus xz plus yz. Notice that we have a common factor of quantity x, y plus xz plus yz across all terms. We can factor this out to get quantity x squared plus y squared plus z squared times quantity x, y plus xz plus yz. Now, we need to express this in terms of the elementary symmetric polynomials. For 3 variables x, y, and z, the elementary symmetric polynomials are s1 equals x plus y plus c, s2 equals xy plus xz plus yz, and s3 equals xyz. We already found our expression in the form quantity x squared plus y squared plus z squared times s2, where s2 equals xy plus xz plus yz. We also know that x squared plus y squared plus c squared can be expressed using s1 squared minus 2 times s2. So, our final answer is quantity s1 squared minus 2 times s2 times s2, which simplifies to s1 squared times s2 minus 2 times s2 squared. And there we have it. We've successfully expressed the complex polynomial s in terms of the elementary symmetric polynomials s1 and s2. This technique is very powerful for simplifying and analyzing symmetric expressions. Welcome to our mathematics tutorial, where we will learn about homogeneous and symmetric polynomials. These are important concepts in algebra that you'll encounter in higher mathematics. Let's first understand what a homogeneous polynomial is. A polynomial is called homogeneous if all of its terms have the same degree. For example, in the polynomial a to the 5th power plus 5a to the 4th times b plus 10, a squared times b cubed plus 10, a times b to the 4th plus 5, a times b to the 4th plus b to the 5th power. Every term has a total degree of 5. Now, let's learn about symmetric polynomials. A polynomial is symmetric if exchanging any two variables does not change the polynomial. In other words, if we have a polynomial p of a and b, then p of a and b equals p of b and a. This means the polynomial remains the same when we swap the variables. Let's look at our first example. We need to determine if the following polynomial is homogeneous and symmetric. 7a to the 4th minus 3 a cubed b plus 7b to the 4th minus 3ab cubed. First, let's check if it's homogeneous. We need to look at the degree of each term. The first term has degree 4, the second term has degree 4, the third term has degree 4, and the fourth term has degree 4. Since all terms have the same degree, this polynomial is homogeneous. Now, let's check if it's symmetric. We need to verify if p of a, b equals p of b, a. So, p of a, b is 7a to the 4th minus 3 a cubed, b plus 7b to the 4th minus 3ab cubed. When we swap a and b, we get p of b, a, which is 7b to the 4th minus 3, b cubed a plus 7a to the 4th minus 3ba cubed. Let's rearrange this to 7a to the 4th plus 7b to the 4th minus 3 a cubed b minus 3ab cubed. Comparing p of a, b, and p of b, a, we can see that they are equal. Therefore, this polynomial is symmetric. Let's move to our second example. We need to determine if the following polynomial is homogeneous and symmetric x to the 5th minus 2x squared, y squared plus y to the 5th plus 12. First, let's check if it's homogeneous. We need to look at the degree of each term. The first term has degree 5, the second term has degree 4, the third term has degree 5, and the fourth term has degree 0. Since the terms have different degrees, this polynomial is not homogeneous. Now, let's check if it's symmetric. We need to verify if p of x, y equals p of y, x. So, p of x, y is x to the 5th minus 2x squared, y squared plus y to the 5th plus 12. When we swap x and y, we get p of y, x, which is y to the 5th minus 2, y squared, x squared plus x to the 5th plus 12. Let's rearrange this to x to the 5th plus y to the 5th minus 2x squared, y squared plus 12. Comparing p of x, y, and p of y, x, we can see that they are equal. Therefore, this polynomial is symmetric, even though it's not homogeneous. Let's examine our final example. We need to determine if the following polynomial is homogeneous and symmetric. 4x cubed, y squared minus 2, y to the 5th plus 3x to the 5th. First, let's check if it's homogeneous. We need to look at the degree of each term. The first term has degree 5, the second term has degree 5, and the third term has degree 5. Since all terms have the same degree, this polynomial is homogeneous. Now, let's check if it's symmetric. We need to verify if p of x, y equals p of y, x. So, p of x, y is 4x cubed, y squared minus 2y to the 5th plus 3x to the 5th. When we swap x and y, we get p of y, x, which is 4y cubed x squared minus 2x to the 5th plus 3y to the 5th. Let's compare this with our original polynomial. We can see that p of x, y does not equal p of y, x. Therefore, this polynomial is not symmetric, even though it's homogeneous. Let's summarize what we've learned about homogeneous and symmetric polynomials. A polynomial is homogeneous if all of its terms have the same degree. A polynomial is symmetric if exchanging any two variables does not change the polynomial. As we've seen in our examples, a polynomial can be homogeneous and symmetric like our first example, not homogeneous, but symmetric like our second example, homogeneous but not symmetric like our third example, or neither homogeneous nor symmetric, not shown in our examples. These properties are independent of each other. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.